So we've built a couple Maclaurin series, but now it's time for the much more difficult task of building a Taylor series. That's right, one that's centered around a different value besides 0. Okay, so first thing we have to do is work on our coefficients, just like in the last problem. We have to kind of figure out the pattern, and hopefully there will be one, of the 0th derivative, the first derivative, and so on. So if we look at the 0th derivative, in other words the function, it's the natural log of x, and the 0th derivative at 2 is the natural log of 2. And then we'll start with the first derivative. First derivative of natural log of x is 1 over x, also known as x to the negative 1. And the first derivative at 2 would be 1/2. Second derivative would be negative x to the negative 2, i.e. negative 1 over x squared. So the second derivative at 2 would be negative 1 over 2 squared, which is 4. All right, third derivative would be, bring the 2 down, so 2x to the negative 3, in other words 2 over x cubed. So the third derivative at 2 would be 2 divided by 2 to the third. In other words, well, let's just leave it like that. 2 over 2 to the third. Of course, you can reduce it. I think I will. I'm going to make it positive 1 over, actually it's over 2 squared, which is 1 over 4 again. All right, fourth derivative. We don't have enough yet for this pattern, so you got to kind of see how this is going to work. So this is going to be negative 6 x to the negative 4, which is negative 6 over x to the 4. So the fourth derivative at 2 would be negative 6 over 2 to the 4. Interesting. And then, of course, you could reduce, but I'm not going to because I think I see the pattern. So this would be 24x to the negative 5, or 24 over x to the 5th. So the fifth derivative at 2 is 24 over 2 to the 5th. All right, now remember, we're trying to come up with a pattern where this is k equals 0, this is k equals 1, k equals 2, 3, and so on. And that'll help us develop our coefficients, right? So the coefficients are going to come out of the patterns that we're seeing here. All right, so those CK coefficients would be, now let's look. Well, if we look over here at the X ones first, we can see a certain pattern arising, right? So if you think about the numbers, it's 1, it's 2 times 1, it's 3 times 2 times 1. Here. This is 2 times 1. This is 3 times 2 times 1. And then this is 4 times 3 times 2 times 1. So there's a pattern with those numerators that's staying even when we put in 2. So what we're seeing is, well, first of all, it's alternating. So I'm going to need negative 1 to a power. Now, if I put in k, let's see, negative 1 to the k would get me negative. No, that's not going to work. So I need it to be plus 1. That way, when I put in 1, it makes it positive because 1 plus 1 is 2. So negative 1 squared would be positive. But if I put in 2, 2 plus 1 is 3. That's odd. That would get me negative. So that'll work for the alternating part. Obviously, there's a fraction part. I have x to the k in the denominator. So you can see x to the 5th, x to the 4th, x to the 3rd. So that's rather obvious there. And then the pattern here for the numbers is 0 factorial, 1 factorial, 2 factorial, 3 factorial, and so on. So it's this number 5, take away 1, which make it 4 factorial. 4, take away 1 is 3, 3 factorial. 2 factorial, 1 factorial, 0 factorial. And of course, this one's kind of unique. It's off on its own. But other than that, this is going to work. So we'll say k minus 1 factorial. But that'll only work for 1 to infinity. For k greater than or equal to 1. right? It won't work for k equals 0. K equals 0 has this unique value right here. Okay, so then when I put in 2, these are kind of the generic coefficients at x, but when I put in, let me just do it this way. When I do the 2 value, it's going to be negative 1 to the k plus 1, k minus 1 factorial, and then 2 to the k, because that's the specific x value we're looking at. And again, it's for k greater than or equal to 1, because k equals 0 is kind of unique. We'll just make a little note. And that can sometimes happen, that your first value doesn't quite fit your pattern, especially with things like logarithms. All right, so now that we have a sense of what the coefficient piece is, we're going to use that piece in order to substitute into our formula. And remember that the way we wrote this was actually calling it the kth derivative at 2, right? Whereas this is the kth derivative at x, right? All right, now if we take the kth derivative at 2, which is these values, and we substitute them into our formula. So develop. So we figured out the coefficients. Now we need to develop the Taylor series, which is a special kind of power series. All right, so we know that the natural log of x is equal to, and let me just write out the formula. It says from 0 to infinity, the kth derivative at 2 over k factorial times x minus 2 to the k. This is the general Taylor series formula. And it's not going to quite work perfectly for us. I mean, it is going to work, but what we're going to have to do is break off the k equals 0 term. So we're going to have to make an adjustment. So we're going to adjust for the fact that that first one is not quite right. And we're going to put in the 0th term at 2. And I won't have to worry about the rest of it because it would be 0 factorial at x minus 2 to the 0, and anything to the 0 power is 1. So it kind of doesn't matter. So, I mean, if you want, you can say over 0 factorial times x minus 2 to the 0, but it's not going to make any difference because that's all going to go away. And then what we're going to do is make an adjustment because the pattern we developed up above starts at k equals 1. So we're going to start it at 1 and go to infinity rather than 0 and go to infinity. So 1 to infinity, and then the pattern we developed was negative 1 to the k plus 1 times k minus 1 factorial divided by 2 to the k, and that all gets divided by k factorial in the formula. Right, there's that k factorial right there. So here's the pattern we developed for fk, or the kth derivative of f at 2. And then we multiply the whole thing by x minus 2 to the k. Like that. Okay, well, this part is easy. We know that this is the natural log of 2. I mean, we already found it up above. So this will be the natural log of 2 plus, and we have to do just a little bit of, well, simple algebra here. So we have to go from k equals 1 to infinity. I'm going to rewrite this. This is negative 1 to the k plus 1, k minus 1 factorial, divided by 2 to the k, and that's divided by k factorial. Okay, so now you can see it. We got to flip and multiply. Or hopefully you can see it. It's negative 1 to the k plus 1 times k minus 1 factorial over 2 to the k times 1 over k factorial, all times x minus 2 to the k. Okay, well, what's going to happen here, the k minus 1 factorial and the k factorial are going to cancel and just leave you k, because this is k times k minus 1 factorial. right? So it's k, k minus 1, k minus 2, and so on. And this was k minus 1, k minus 2, and so on. And so they all go away and just leave you a k sitting there. And so it's negative 1 to the k plus 1 over 2 to the k times x minus 2. Except we don't know what the interval is. Oh. Negative 1 to the k plus 1 over 2 to the k times k, all times x minus 2 to the k, 4, and we don't know the interval yet. That's what we're going to figure out on the next page. Speaking of which, we're going to need a test to find this. So I see, I mean, we have options, but why not use the ratio test? It works really well for us. So let's use that ratio test. So r is equal to the limit as k goes to infinity, absolute value. It's ak plus 1 divided by a sub k. So a sub k plus 1 would be negative 1 to the k plus 1, which is k plus 2, over 2 to the k plus 1 times k plus 1, all times x minus 2 to the k plus 1. And then we divide that by what we had, negative 1 to the k plus 1, 2 to the k times, actually, just for the sake of making things easier for ourselves, because we're going to have to divide all this anyway, let's put the times part out here, or up in the numerator, because that's where it belongs. So this will be k plus 1 here, and then this will be x minus 2 to the k right here. All right, so that's the limit as k goes to infinity. We get to write it all again. So it's negative 1 to the k plus 2, x minus 2 to the k plus 1, over 2 to the k plus 1 times k plus 1, times 2 to the k times k, over negative 1 to the k plus 1, x minus 2 to the k. And thank goodness for the ratio test. All sorts of stuff is going to go away. Oh, let's see. So, well, the negatives are kind of irrelevant anyway, because of the absolute value. So you can kind of just knock them out of there. I mean, technically, you're left with a negative 1 right here, but it won't make any difference because you're inside an absolute value anyway, so who cares? Then you have the 2 to the k and the 2 to the k plus 1, which is just going to leave you a 2 down there. Then you have x minus 2 to the k plus 1, x minus 2 to the k is just going to leave you x minus 2 right up here, and then k over k plus 1. All right, so let's rewrite that. So this is the limit as k goes to infinity. I have a negative 1 times x minus 2 times k over a 2 times a k plus 1. All right, well, the only parts that involve k are the k and k plus 1, so the rest of it can come out, and the negative is irrelevant because you take the absolute value. So what I can do is say absolute value of x minus 2 over 2. I do need to keep the absolute value here for the x part because I don't have a guarantee of x being positive, but 2 is definitely a positive number. I learned that a long time ago. Limit as k goes to infinity of k over k plus 1 in absolute value. All right, well, we know this because of L'Hopital's rule, right? That's infinity over infinity, so L'Hopital's rule tells us that we can take the ratio of the coefficients. Well, technically you take the derivatives, but we learned that there's a little trick for that when it's a rational function, i.e. a polynomial over a polynomial. Actually, I'm just going to write it over here. So this is the absolute value of x minus 2 over 2 times 1. right? Because of L'Hopital's rule. And it's a table in it's in chapter 10, that you can take the ratio of the coefficients when the polynomials have the same degree. All right, now remember, in order to be convergent, we need this to be less than 1. So we need the absolute value of x minus 2 to be less than 2, right? Because you multiply both sides by 2. And that means that negative 2 is less than x minus 2, which is less than 2. And then we add 2 to all parts of that double inequality. And we get 0 is less than x, which is less than 4. There's our interval of convergence. But as always, we need to check our endpoints because we don't know. Let's do it right here. We don't know if one of these has an or equal to sign on it. All right, so let's let x be 0. If x is 0, then my series, I don't want to worry about the natural log of 2 part. I'm just going to worry about the 1 to infinity part. Would be negative 1 to the k plus 1 over 2 to the k times k. And then instead of x minus 2, right, it'll be negative 2 to the k. Well, let's see. That's k equals 1 to infinity. That's negative 1 to the k plus 1 times negative 1 to the k times 2 to the k over 2 to the k times k. All right, well, let's see here. That's going to be gone. 2 to the k's are gone. And it leaves you negative 1 to the something or other, right? We just need to figure out if it's alternating or not. And the answer is it's not. So this is k plus k is 2k. So this is k equals 1 to infinity, negative 1 to the 2k plus 1 over k. That is actually always negative. That never changes because that's odd. 2k plus 1 is odd. So 1, 3, 5, 7, and so on. So this is always negative 1. So that's the same thing as saying the series from 1 to infinity of negative 1 over k. Or in other words, you could put the negative out in front right here and say 1 over k. That would work too. And that's the harmonic series. It's the negative of the harmonic series, but it's not alternating, it's just negative. So that's the negative harmonic series, and it diverges. It's the harmonic series, but every term is negative. Okay, so it still diverges. I mean, the harmonic series diverges, therefore it does when it's negative also. All right, now if x is equal to 4, then we have the series k equals 1 to infinity, negative 1 to the k plus 1, 2 to the k times k, and then I'll have a 2 to the k, because 4 take away 2 is 2. Okay, well, that's gone. And that leaves you k equals 1 to infinity, negative 1 to the k plus 1, but that alternates. That's positive, negative, positive, negative. It's not always negative like that other one. Over k. So this is the alternating harmonic, and it converges. Alternating, there we go. Harmonic, it converges. Therefore, our interval actually has an or equal to on the 4. The interval is 0, 4. And so we should go back a page and state that and put that in right here. As our interval of convergence.